Um, let's construct a matrix P so that its columns are just the eigenvectors of some other matrix A. And we want P to have as many columns as A has. So if there are some, if you have some repeated eigenvalues that you don't get a full set of eigenvectors, we'll just repeat some of them so that we do get n columns, that P has n columns, meaning the same number of columns as A. So that's what P is. Now if I multiply both sides, multiply that P by A. That means multiplying all those K's by A. And each one of these means associated eigenvalue times K. So A times P is this matrix here, where the columns are lambdas times their associated K, eigenvectors. So eigenvalues times their associated eigenvectors, okay? Okay, so far. Now let's say I post-multiply that matrix P by a diagonal matrix where the diagonals are the eigenvalues. Here's what it's going to look like. It's, it's all zeros off the main diagonal, and the main diagonal are the eigenvalues of the original matrix A. I do this matrix multiplication, and you have to go back to ways we can do matrix multiplication. There was one particular block method where each K here is a column vector. I can break this up as a column vector times a row vector, a bunch of those sums from 1 to n. So this product is K1 times this top row plus K2 times the second row, etc. Which then means this, which then means this. But this is just A times P. So this is a true statement. P times D, this D, equals A times P. Now, one step further. If all the eigenvectors are linearly independent, then P is invertible. If A has n linearly independent eigenvectors, P is invertible. And then I can pre-multiply by P inverse on both sides here, and I get this little relationship. This P is called the diagonalizing matrix. It's something you do to A to get a diagonal matrix. And the P's will be made up of the eigenvectors, and the D is the eigenvalues in the same order. So I'll just finish this in this video because it's the last video of my whole course here. So if we can find an n by n non-singular matrix P such that this is true, if we can, we call that the process, we call that diagonalization. The necessary and sufficient conditions is A is diagonalizable if and only if A has n linearly independent eigenvectors. It would be sufficient if A has n distinct eigenvalues, then you know all n eigenvectors are linearly independent. That's how you know if such a P even exists. And if it does exist, you construct it this way. Each column of P is an eigenvector of A. And then D is just a diagonal matrix made up of the eigenvalues in the same order as the K's. You never actually do this computation, for this purpose anyway. Our job is to find P and then D, to find them both, P and D, you don't actually need to carry out this matrix multiplication or this inversion and all that stuff. P is found this way, D is found from the eigenvalue, like this case here. You find the eigenvalues, you find they are distinct, 0 and 6. Two real eigenvalues distinct, so it's diagonalizable. Go ahead and find the eigenvectors. That's where all the work is, finding the eigenvalues and then the eigenvectors. And we find these two eigenvectors, 5 minus 4 and then 1 minus 2, corresponding to 0 and 6 for the eigenvalues. So P has those two columns, 5 minus 4 and 1 minus 2. This one came from lambda 1. So when the D must be in the same order. Lambda 1 is 0, lambda 2 is 6. 6 corresponds to this guy. All right? This also helps if we're dealing with an A matrix that's already diagonal. If you remember, we did this guy and kind of did it the more tedious way of finding the determinant of A minus lambda I. But you know it's diagonal. So you can find the eigenvalues is really easy. They're going to be 0, 0, and 1. And since it's already diagonal, the P is just, the eigenvectors are just the identity. P is the identity. So the eigenvectors are just the columns of the identity matrix. And we could find the eigenvalues and the eigenvectors of this A really easy. We didn't need to take a determinant and all that stuff. So anyway, that's diagonalization, and that's the last subject of my course that I call linear algebra. One final word. Gilbert Strang is the expert, the guru, the saint of linear algebra. His lectures are on YouTube, and I recommend them. They're insightful. He's kind of fun to watch. But I found that you needed to already have a fair amount of knowledge to be able to follow his lectures. At least I did. So that's why I did this course. You can follow him directly, do it. If you need to start with baby steps, then look at my video. Anyway, that's the end of this course.